On April 20, 2004, a 30-meter deep excavation collapsed in Singapore, claiming 4 lives and swallowing a massive section of the Nicoll Highway. This wasn't just a tragic accident, it was a multi-million-dollar engineering catastrophe driven by a fundamental misunderstanding of mathematical non-linearity. In our previous video, we deconstructed how the tangent stiffness matrix erodes near geometric instability and how boundary condition sensitivity turns stable models into deadly traps. Today, we apply those exact high-fidelity concepts to the Nicoll Highway collapse. This is not merely a case of human error, it is a masterclass in the fatal failure of stiffness negotiation in deep excavations. Welcome back to Strong Foundation Engineering. Grab your notebooks, let's dive into the mathematics of disaster. Let's start with the geotechnical precondition. The site was a 30-meter deep excavation in the Calling Formation, specifically marine clay. The engineers used method A, a total stress analysis. In Plaxis, they assumed the undrained shear strength scaled linearly with depth. But here is the nonlinear error. Calling marine clay exhibits severe strain softening under shear. As the excavation progressed, the constitutive matrix degraded rapidly. However, the computational model kept using the pre-yield stiffness. By treating the clay as a linear elastic medium for far too long, the designers grossly underestimated the massive wall deflections. They ignored the physical reality of the soil's yield surface. The crucial lesson here is simple mechanics. When the soil softens, the load must go somewhere. As we established in our previous discussion regarding the constitutive matrix, if your computational model fails to capture the material nonlinearity of the clay, your predicted wall deflections are entirely meaningless. The soil was yielding, shedding its load onto the retaining structure, but the computer screen showed a safe, elastic world. This disconnect between numerical assumption and physical reality set the stage for the progressive collapse. Now let's look at the smoking gun. Connection 130. Remember how we discussed that interface stiffness and boundary constraints are state-dependent? At Nicoll Highway, the strut-to-waler connection was the critical boundary. In the finite element model, connection 130 was idealized as a perfectly rigid boundary. But in physical reality, this connection lacked crucial web stiffeners. Without these stiffeners, the immense compressive loads triggered local web crippling. The connection didn't just bend, it completely buckled. This missing stiffener led to a classic geometric nonlinearity, an instability in the geometric stiffness matrix. Because of local web buckling, the support condition shifted from a fixed boundary to a free one almost instantaneously. Connection 130 lost its load-carrying capacity in a fraction of a second. It converted a highly stable compression strut into an eccentric mechanism, violently shedding millions of newtons of force into the neighboring structural members. The matrix didn't just degrade, it shattered, but the structural connections weren't the only victims of bad assumptions. Let's look at the jet grout pile, or JGP layer. This layer was designed to act as a massive temporary strut in the soil to limit the retaining wall's toe from kicking out. In the finite element model, the JGP was represented as a continuous, high-stiffness strut, perfectly embedded within the soil matrix. But forensic reality tells a different story. In the field, underground utility obstructions prevented continuous grouting, creating physical gaps. We call this a stiffness void. Here is stiffness negotiation in action. When the massive soil load tried to negotiate its path through the ground, it encountered these gaps. The local stresses bypassed the JGP completely and surged directly into the 9th level of the steel struts above. Because those struts were already severely compromised by the boundary condition sensitivities we just discussed, they couldn't handle the surge. The load negotiated away from the intended support and found the weakest link. The entire system instantly entered a fatal, progressive collapse regime. But perhaps the most tragic error occurred in the site office. During construction, field inclinometers showed massive wall deflections far exceeding predictions. To justify this, the engineers performed back analyses. They engaged in the ultimate numerical fallacy. They manually inflated the soil stiffness parameter E in their software to force the linear model to match the nonlinear field data. They treated active plastic yield as a simple elastic calibration error. They completely ignored the mathematical reality that the tangent stiffness matrix was driving toward singularity. If the matrix is approaching singularity, you don't fix it by artificially inflating stiffness. You recognize it as the mathematical signature of impending rupture. The human limitation here is profound. The failure at Nicoll Highway wasn't a lack of instrumentation, it was interpretation latency. The sensors were screaming that the system was nonlinear, but traditional finite element analysis couldn't update fast enough to warn the engineers before the collapse. We are currently limited by the speed of human-in-the-loop FEA updates. We can explain the collapse beautifully after it happens, but we struggle to predict it as it happened. So here's the question for our next video. How can we bridge this insight gap and update the global stiffness matrix in real time? In our next video, we move beyond manual back analysis and enter the world of physics-informed neural networks, pins, and agentic workflows. We will explore how AI can ingest live sensor data to predict mathematical divergence before the first crack even appears. Subscribe so you don't miss it, and stay engineered.